In the previous lecture, we studied when we have positively charged hollow cylinder and we want to find what is the net electric field inside it, and we got the result by applying the Gauss Law argument. Today we will take another scenario. The situation is same, the scenario is different. The situation is we have a positively charged hollow cylinder and we have placed it in this manner. The axis, about this axis, we have drawn the Gaussian surface. So this one is Gaussian surface. And we have taken the length of that Gaussian surface, a Gaussian cylinder. The length of this Gaussian cylinder, which is the enclosed three-dimensional enclosure, that we have taken cylinder. Why? Because it is cylindrical. It is symmetrical over the cylindrical axis. Well, so now we assume the distance, which is the point of interest. Here's the point wherein we want to find what is the net electric field. Well, the given information is the hollow cylinder that is charged positively is of radius capital R, and the linear charge density is given as lambda, which means that this is just increasing lengthwise, right? This part, the radius is constant. The only increase is in length, and that's the reason that we are considering as linear charge density lambda. So what should be the approach to find a scenario, for the scenario when we have this small r greater than the radius of the cylinder? So we'll look into this Gaussian surface and try to find out how many surfaces it has. So it has two flat surfaces, one we have curved surface. So if you want to write, you can write this entire closed surface. If you want to find in this closed surface what is the net electric flux, so this is going to be E dot dA. Now this net flux, by the very definition, is including the flat surfaces, two flat surfaces and curved surfaces. And by our argument, if you remember in the previous lecture, we argued that if this is the situation, then where's the electric field, what kind of electric field we get above and below portion of it. Symmetrically, we find the electric fields going outward radially in this way. And obviously here also it would be electric field that would be directed downwards, radially out, if you find the symmetrical axis to be a cylindrical symmetrical axis. Well, if you take the dA, which is the elemental area on this curved surface anytime, and we have taken the radius of this Gaussian cylinder that we have assumed is r, small r. So here we can write r, we have taken is radius of the Gaussian cylinder. This is what we have assumed. With this information, now we can say that this the surfaces that we have, one is flat, the another one again is flat, and the area vector here, if we are going to find the area vector of this portion, is going, direction of electric field is going outward. Similarly, for the lower portion, it would be radially out downwards electric field, and any area that you are going to take will be facing this way, right? dA1 we have taken for an example. So by our, and dA1 is going to be 90 degrees, and we know this equals what? This equals, for the curved, we can assume this to be, this area to be dA2, for example. So this includes, this particular thing includes curved integral over curved surface plus twice of the flat surface. So we can write this E dot dA, we have taken 2 here, plus for the two flat surfaces, and we know both the quantities are going to be equal, right? So the quantities are going to be equal, so we can take this twice of electric field E plus dot dA1, and this is for the flat surface. Now if you want to find what is, so this entire thing is going to be this plus this. So now if you want to find what comes out of it, so we'll just operate this dot product. You would get curved, it would be d magnitude of E magnitude of dA2 and cos. So what is the angle when we take curved surface? It would be cos 0 degrees, plus twice of, for the flat one, integral, it would be magnitude of E magnitude of dA1, and here we'll get cos 90 degree. So cos 90 degrees is 0, so this goes, entire expression goes 0. So what we conclude? We conclude that whatever net flux is that would be there, it will be E dot dA, and this E dot dA would just be equal to E dA2 cos 0. Well, this is the conclusion. Now we'll continue our calculations here. Now we are, after knowing this, we'll now apply Gauss law. So by Gauss law, what do we know? By Gauss law, we know that this net flux that we have calculated, this net flux, which is E dot dA, is equal to the net charge enclosed. Now we have this linear charge density as lambda, and we want to find what is the net enclosed. So lambda is what? Lambda is charged enclosed per unit length, and the length we have taken L. So if you want to find the total charge, so charge per unit length is lambda. If you multiply lambda with L, you will get the net charge enclosed. So this comes out to be lambda L in the numerator, and we know this is divided by epsilon naught, which is electrical permittivity of free space. And from this expression we know that this is just equal to, the net flux is just equal to E dA2. Why? Because cos 0 is 1. So we are left with this expression. So therefore from this expression we can write that this equals curved E dA2. That is what? The magnitude of E multiplied by magnitude of dA2 should be equal to lambda L over epsilon naught. This is what we conclude. So E is constant over it, right? E is constant all along the surface of it. Well, if E is constant, we'll pull it out of the integral sign. And what is dA2? So dA2 is the entire curved surface area. So from our understanding, we know that what is the total curved surface area if you're going to integrate, it comes out to be 2 pi r. R is the radius, that is the capital, that's the small r, sorry, that's the small r is the radius. So we get here lambda times L should be equal to E times 2 pi r, small r L. Okay, and this comes out to be lambda L over epsilon naught. So from here, therefore, we get E is equal to, L gets cancelled out, and we get lambda divided by 2 pi r epsilon naught. So this is what we get as net electric field because of this hollow cylinder, positively charged hollow cylinder, and with a radius capital R. So we get here electric field at point P, this P is equal to, and this P is at a distance small r, so this is at a distance r, which is constant over it, r, small r, epsilon naught. So we conclude from this that this is the electric field at point P. the net electric field. That is how we have applied the Gauss law in this question, and this is another scenario. We can name it this scenario as B. First scenario wherein we considered the point P, the point of interest inside it, we did in the previous video. This is a continuation part of that. So take note of this. It's going to help you to understand the approach, how we apply the Gauss law when we have this situation. So watch the next video for the solid cylinder. We want in the next video we want the electric field because of the charge, positively charged solid cylinder having a particular radius. We'll take that scenario in the next video. Thank you.